All right, let's move on to the next example. So the next example we're looking at is question 10, right? And in question 10, again, we're looking for the area, and the area is between the curve y equals x cubed. We've got the x-axis. We have two lines, the line x equals -3 and the line x equals 2. Remember, these two lines here, they're both vertical lines, so they're giving us the boundary of our integration. So let's integrate that. Oh no, let's sketch it first. That's always the first thing to do. Sketch it. X, Y, doesn't need to be a Picasso. I know, and you ought to know by now, that a cubic looks something more like that. Oh, excuse me. There's our y equals x cubed. Here's the x-axis. We've got x equals -3, so there's going to be a chunk down here at x equals -3, and there's going to be x equals 2, so there's a straight line that goes up here. There's x equals 2. And I know that my graph is not symmetrical. The point is not perfection. The point is to give you a visual image of what we're trying to work out here. And if we work out these two areas here, I forget exactly what the question requests, but if it's trying to find out the area that's bounded by this curve and the x-axis, then we need to work out both of these areas separately, because this will come out as a negative value and this will come out as a positive value. And those two things will start to cancel out. But if we want the actual absolute area, the absolute value for the area, we need to find out the absolute value of that area and add it to the value of that area. So let's assume that that's what we're doing. Okay, and so we're going to have limits from -3 up to 0. That'll be the first integration. So the area is going to equal this function here, x cubed. We're integrating with respect to x. We're going from -3 to 0. Then we're going to do this section here, the second bit, which is from 0 to 2 for this same function. This should actually end up giving us a negative number. So the way we get around that, I've already mentioned it, is we take the absolute value. Absolute values give us the magnitude of something, the size of something. That's what we want, is the size of this thing. And then we're going to add the size of this thing to that. Now, the integration is very simple. That's going to be x to the power of 4 on 2. And for this chunk, it'll be from -3 to 0. Then we add this bit, which will be x to the power of 4 on 2. And it'll be from 0 up to 2. From 0 up to 2. Excuse me. And when I put this all together, we'll end up having, again, absolute value signs are going to go in there. Yeah, from 4. Gosh, sorry. I don't know why I put the 2 in the denominator. You guys have probably already picked up that that was an error. This denominator here should be a 4, and so should that denominator. I don't know why I did that. Right, let's evaluate these two integrals. So we'll have 0 on 4, 0 to the power of 4 on 4 minus -3 to the power of 4 on 4 plus, over here we'll have 2 to the power of 4 on 4 minus 0 to the power of 4 on 4. And clearly 0 to the power of 4 is just going to be 0, and 0 over 4 is 0. So that makes things a little bit simpler for us. But it would seem that we're going to have a negative value inside this bracket, because that would be -3 to the power of 4, which I think we discovered earlier was 81. So 81, but because we've got absolute value signs, it'll be the absolute value of -81 on 4 plus 16 on 4. And this is going to be 20 and 1/4 plus 4, which gives us 24 1/4. That's what the area would be if they're looking for the area enclosed by the curve and the x-axis from here to here.